This is Daniel Coosbury, and we're still looking at some more complicated probability problems. And this video is going to focus on some counting techniques that we're going to use probably in a different video to do some harder probability problems that would involve having to count a lot of things. And let me kind of show you what I mean when we say needing to count things to find probability. So I have an old definition from a previous video of how we would find probabilities of an event that has a certain number of equally likely outcomes. And so we've used this a lot. The probability that event A happens is the number of ways A can happen, so the number of different outcomes that would make the event happen, over the number of outcomes in the sample space. And where counting comes into play is in this phrase, number of outcomes. Number of outcomes in A and number of outcomes in the sample space. We're going to see some problems where the number of outcomes is actually just very, very, very large and actually kind of hard to find without these counting methods. So there could be, hundreds of different ways A can happen, and to find the probability of A, we need to come up with the exact number of ways A can happen and the exact number of outcomes, which are going to require some mathematical methods used for counting big things. So now that I've probably sufficiently scared you, let's go ahead and look at some of these methods. I think you'll like some of these, and then there are going to be some that are going to seem real similar, and we'll try to distinguish. So let's start with the fundamental principle of counting. The fundamental principle of counting says that if you have an operation that can be formed in m different ways, so this is a number, m, and another operation that can be performed in n different ways, so different number. So you have two things going on, and one can happen in a certain number of ways, the other can happen in a different number of ways. The total number of ways to perform the sequence of two operations, so both of them one after another, is going to be m times n. So you take the number of ways the first one can occur times the number of ways that the second can occur, and that's how you get the total number of ways it can happen. In general, if a sequence of several operations is to be performed, the number of ways to perform the sequence is found by multiplying together the number of ways to perform each individual operation. So that's a pretty in-depth sounding definition. And I'm going to give you two examples to show you this scary definition is actually not too bad. Okay, so here we have a certain automobile that can be available in any of three colors. So think of this as an operation. We can have a red color, we can have a blue, or we can have a green. And we can also get a vehicle with either a large or a small engine. And then the question is, how many different ways can the chooser buy a car? Well, let me go ahead and start by listing this thing. So we can get a red car. That's an operation. We can get a blue car, or we can get a green car. And for each one of these, we could either get a small or a large engine. Here's another tree diagram, which means that we have a grand total of 6 different ways to get a car. We can get a red car with a small engine, a red car with a large engine, a blue car with a small engine, and so on, based on this diagram. So where this counting rule comes into play is if you think about buying a car, we've got 2 different things that we can get in this car. We've got the color, and we got the engine size. And we know that there are 3 different colors, so think of that as being M. There's 3 different colors, and there's 2 different engine sizes. And so the answer to the question, in how many ways can we choose a car, how many different kinds of cars are available, is going to be 3 times 2. You pick a color, there's 3 of them. Pick an engine size, there's 2 of them. Multiply those together to get the total number of combinations. So there it is on the tree diagram. There it is, using the fundamental principle of counting. So you might be thinking, well, we didn't really need a rule to find this number 6 because the tree diagram worked just fine. Well, here's a more complicated example where we're going to want to use the fundamental rule of counting. License plates in a certain state contain 3 letters followed by 3 digits. How many different license plates can be made? Okay, so now suddenly we're going to have a huge number on our hands, and we're going to want to do this in a pretty methodical way to make sure that we count the number of possible license plates correctly. Okay, so let's just start by envisioning what a license plate might look like. That starts out with 3 letters. So these first 3 boxes are blanks are going to be letters. The next 3 blanks are going to be the 3 digits. And we're going to think of these 3 spaces, or really all 6 of them, as different operations. So how many things can go here? How many different things can go here? And then to find our answer, we're going to multiply all these things together. And let me use a different color. So my question then is, how many different letters can go in this first space? Well, there's 26 letters, so 26. There's 26 different things that can go there. So now my next question is, how many different letters can go in the second space? Well, what if I put like the letter A here? Does that mean I can still put the letter A here? And the answer is, of course, yeah, we can still put the letter A here. We can put any letter we want here, regardless of what's there, so that we can put 26 letters in the second space and 26 letters in the third space. So we've already got 3 of our different ways, the number of different ways we can perform these operations. Okay, now let's do the digits. How many different digits can go here? Well, if you're counting 1 to 9, that's 9 digits. You add 0, which is an option. We have a total of 10 different digits that can go here. So if the number is 0 to 9, there's 10 of them. And then in the same way that you can repeat digits and whatnot, you can put 10 digits there and 10 digits there. So my answer to how many different license plates can be made is found by multiplying those 6 numbers together. And so I'm going to do that real quick, and we're going to see a pretty large answer. And this is why we needed the fundamental rule of counting to begin with. So 26 times 26 times 26 times 10 times 10 times 10. And I get the number, well, that's a big number, 17576 with 3 zeros. 17576 with 3 zeros. Let's put some commas there. 17,576,000. Now here's the thing, that's a huge number and it's an intimidating question, and using the fundamental rule of counting, we found the answer in about 3 minutes. That's kind of nice. So this is how you do problems that involve a different number of operations happening one after the other, and your job is to identify how many different ways can each one occur and then multiply them together. Okay, so that's what I really like, this visual of making blanks. So I even made blanks for the engine color, I'm sorry, the car color and the car engine. I like making blanks and then multiplying those numbers together. I think that's a really nice way of doing these problems. So these are the ones with the number of operations, or you've got sequential operations happening one after the other. Okay, so let's look at another kind of counting problem. This one's a little bit related to the last one, and we're going to have to distinguish them from this point out. I've got 4 of these, so this is the second one. We can also count the number of permutations of n items. So if we have a certain number of items, the word permutation means ordering. We're counting how many different orders can we put a certain number of items in. And the number of permutations has a really nice formula. So if you've got n items, the number of permutations, the number of different ways that you can order, so when you see permutations, think order. The number of different ways you can order n items is given by what's called n factorial. So this exclamation mark is the word factorial. That's what the exclamation mark is. Factorial means if n is a counting number, so like 1, 2, 3, 4, 5, it's a whole number. Factorial means multiply by all the counting numbers that are less than that. So take n, multiply it by the number less than that, and the number 1, 2 less than that, and then so on all the way down to 1. That's what n factorial is. You might have seen this in some math class before. But this is nice because it gives you the different number of orderings you can do with n items. And so I'll do a small version of this problem. We have 5 runners running a race. One of them will finish first, another will finish second, and so on. And how many different orders can they finish? Well, I'm going to do this using my little blanks and then show you how this formula would also give you the exact same answer. So I'm going to use kind of that fundamental rule of counting and talk you through why this works a little bit different than the license plate problems. Okay, so this is going to be first place, second place, third place, and so on. And let's just say that I've got all my runners, they're still in the race, and let's just say they all have an equal chance of ending up first or whatever. So if I've got 5 runners still in the race, how many people, what's the number of people that could finish in first? Like how many different possibilities are there? Well, there's 5 in a race, which means that 5 people, one of those 5 people is going to end up here. So I've got 5 different options of people to put here. Now let's say that somebody's already finished first and the second place thing is up for grabs. How many people are left that could end up in the second place slot? Well, there are 5 runners. One of them's already finished. So there's 4 options left for the second place. So now there's 3 people left in the race, and only one of them could end up in third place, but there's 3 different people who can end up here, and so on. There's only 2 people left in the race. And then once 4 people have finished, there's only 1 person left. There's only 1 person who can end up here. I might have said that in a really confusing way, but what I'm trying to point out is once you pick the first place spot, there's only 4 people left for the second place spot, and so on and so on. And you can use the multiplication rule. I'm sorry, that's not the multiplication rule. You can use the fundamental rule of counting to get that answer. Also, it's worth noting that this is what 5 factorial is equal to. So 5 is a counting number, it's a whole number. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's what this definition means. So we found the different number of permutations in 2 ways. We use the factorial, and we also could just kind of visualize it by putting a certain number in each place. So this was different than the license plate problem, because the license plate problem, what I put in one blank didn't affect the number in the next blank. Here, once somebody ends up in first, it limits the number of people left for the second place spot. We can't have 5 different people who could end up first and then have 5 different people who could end up second after that. So this is why you start counting down from 5 when you do the permutation of n items. Okay, there's also a way of doing orderings of a certain size group from a total number. So we're going to call this permutations of R items. So this is one number chosen from n, which is the total group size. And this has its own special symbol. Oh man, there's a little underlined thing. The symbol is NPR, little n, little r. This little n refers to the whole group size. The little r refers to the size of the ordering that we want. And this will become clear when I do this example down here. This is the formula for doing this by hand. I'll show you how to do it in the calculator. Frankly, since I learned how to do this in the calculator, I haven't used this formula, but you can use the formula if you want. But this is n. This is the total number of people we're picking out of, and this is the size of the group. So let me show you this one with another race example. We've got 10 runners in a race. So there's 10 total people. That's going to be n. N is 10. The first place finisher will win a gold medal. The second place finisher will win a silver medal, and the third place finisher will win a bronze medal. And how many different ways can these medals be awarded? So let me start by drawing these blanks again. Now I'm no longer interested in ordering the 10 people total. I'm really just care about who wins, who gets second, and who gets third. So you see how I have 3 blanks now instead of 10 like the last example? I don't care about the last 7 people. I just care the different ways that we can have somebody in first, second, or third. Okay, so I've got the number of people in the race is 10. My group size is going to be 3. So I've only got 3 things I'm interested in. R is going to be equal to 3. If I've got 10 people still running a race, kind of like the last problem, the number of people who could potentially end up in first place, sorry about that, this phone's just going to have to ring. The number of people who could end up in first place is 10. And then now that somebody's ended up in first place, there's 9 runners left in the race. There's 9 people who can end up in second place, and 8 people can end up in third place. So this is going to be my answer, 10 times 9 times 8. And I multiply those 3 numbers together to get an answer, so 10 times 9 times 8, and that gives you 720, which is my answer. So you see how this is a little distinct from the last problem. The last problem permuted all of the items, all 5 of them. Here we've got 10, but we only want a permutation of size 3. So there's only three places here. Now let me show you how to do this problem in the calculator. To do this problem in the calculator, we're going to type something that looks a lot like NPR. The goal, we're going to have to put numbers in for N and for R. Our N is going to be 10 for our total number, and then our R is going to be 3 for the group size. So we're going to type in something that looks like that into the calculator. To do it, I want that to go there. To do that, start by typing in the first number, and then I'm going to show you where the P is on here. So type in 10 first, and then go to math, and go all the way over to the probability column. So hit math first, go over to probability, and you see NPR. Click on that. So I've got 10, and then I've got NPR, and then I'm going to put 3 over here. So this is the thing in the calculator that looks a lot like 10 permute 3. Once you hit enter, you get 720. So for more complicated problems with bigger numbers or bigger group sizes, like if this was like, you know, a much bigger number than 3, I might not have done it by hand. You can do this in the calculator. I would suggest doing it in the calculator. So when you're doing an ordering, this is your whole group size. This is the size of the group that you're permuting. And the left number should always be bigger than the right number, and it should give you the right answer when you're getting the different number of orders. So keep this one straight from the last problem where you're permuting the n items. So you're just taking all 5 of them and putting them in order. Here you've got 10 and you're permuting 3. You're getting a permutation of size 3. There's only 3 things here. And let me follow that up with the last way we're going to learn how to count. It's called something called a combination. And this is distinct from permutation because with combinations, we're also reaching into a big group of things. We're pulling out a smaller group, just a certain number of items, and with combinations, we don't care about order anymore. So we no longer have to think, okay, well, who's in first, who's in second, who's in third. Now we're just interested in the group, just how many different combinations regardless of order. So one example of doing this would be if you're playing cards, and let's just say you're playing a 5-card draw. You've got 5 cards in your hand. You don't care what order that you draw the cards in. You just care what's the group of 5 cards in your hand. No particular order. You just have 5 cards in your hand. That would be an example of a problem we would use a combination to find, not a permutation. Like I don't care what card I drew first, second, and third. I just care what are the 5 in order. So it's a different number. We're going to find it differently. This is the formula for combination. You can see this looks a lot like NPR. It's NCR, C's for combination, where N is the total group size and R is the size of the group that I'm pulling out. And as you can maybe guess, this is also in the calculator. So while you can use this formula with factorials, I'm not going to use it. I'm going to use the calculator to find the number of combinations of R objects chosen from N. So when we do it in the calculator, keep in mind, this is the bigger number, this is the smaller number. So I've got a certain event that 30 people are going to attend. So these numbers are getting big now. The calculator is going to be helpful. A certain event that 30 people can attend, and 5 is going to be chosen at random to receive prizes. The prizes are all the same, so the order doesn't matter. Okay, so there's not a first place prize or a second place prize. All 5 prizes are the same, kind of like Willy Wonka's golden tickets. And I don't care who gets it first and who gets it last. All 5 kids in the Willy Wonka story got to go to the same place in the same time. So the order doesn't matter. How many different groups of 5 people can be chosen? And I'm going to simply show you how to do this one in the calculator. So my N is equal to the total number of people here. This is N. And my R is equal to the group size. So I'm choosing 5 out of this group of 30. So I'm going to find this number 30, C5, and I'll do it in the calculator. Just like with permutation, you got to type the first number first. So type 30, then go to math, over to the probability catalog, and hit NCR. It's right there under NPR. And then hit 5. And I get the number 142,506. Which is a huge number, but it's true. There are that many different combinations of size 5 that I can get from a group 40. So that's how you do the combination. So what you've got to keep straight with doing counting problems now are, do I do a combination or a permutation, which is the same question as asking, does order not matter, like with combinations, or does order matter like with permutations? And those will spit out different numbers. If you were to use NPR for this problem, you'd get a different answer and it would be wrong. So keep that straight. Also keep straight the ones that don't involve pulling out a smaller group. So like with the fundamental counting rule one, we're not pulling out any kind of group at all. We're just listing things like that. The only thing I don't think I showed you with counting is I didn't show you where factorial was in the calculator. So we can do 5 times 4 times 3 times 2 times 1 really easily. But if we had like 40 factorial, we do 40 times 39 times 38, so on. That might be too big for the calculator. Let me just show you how to do 5 factorial in the calculator. You type in 5, go to math, go over to the probability catalog. It's the 4th thing. So it's under those other ones. They put them all together. So 5 factorial is equal to 120. That's how you do that in the calculator. So now you have a lot of tools to do some of these big counting problems. What we'll look at in the next video is how to use the counting problems to compute probabilities like I showed you at the start. What we really need them for is how to find the number of events in A and the number of total outcomes. But we're going to have to save that.